Computers are really cool. The earliest known computational device is the abacus, which was invented, I think, between 2500 and 1100 BC in Mesopotamia. And Mesopotamia, it's the beginning of civilization. People need to start keeping track of larger numbers of things than they were evolved to do on their own. So they invented the abacus, which allowed them to store substantial amounts of information as they were doing calculations. So an abacus is just a bunch of rows of beads. Each row represents a power of 10. So you can slide it across and use that to represent numbers. And it adds up quickly. If you have 7 rows, then you can do calculations in the millions. Pretty smart. Then you have devices like the astrolabe, and there's some debate over whether or not this was invented by Hipparchus in the 2nd century BC or by Apollonius in the 3rd century. But basically it's this metal ring with a line in the middle representing the horizon, and there's this disc behind it that you can rotate, and it shows you what the night sky would look like on that day if you looked at the horizon. Then there are devices like the Antikythera mechanism from around 2,000 years ago. It was discovered in 1900 by some sponge divers in the Mediterranean off Antikythera Island, and they found this sunken wreck with a bunch of bronze statues and little treasures. I don't know much about that, but they found the Antikythera mechanism, and it's this device that can be used to calculate the location of the sun and the moon on a specific day. There was this outer ring and this inner ring, and the outer ring could be rotated with a hand crank to bring it to a specific day of the 365 on the calendar, and the inner ring could be rotated to bring you to a specific zodiac sign. So you could bring it to a specific day, and that would rotate 2 arms, one of which had a little sun on it, the other had a little moon, and they would rotate, and once you reached a certain day, it would show you the locations of the sun and the moon on that day. Even cooler, the little bead that they had to represent the moon would spin as you turn the crank. So one side of it was painted, and it would show you the phase of the moon on the day selected as well. So imagine being able to predict the phase of the moon on a specific day 10 years from now. Fast forward 2,000 years, and you have devices like the vacuum tube, which uses the Edison effect, where if you have a vacuum and a cathode and an anode, and you heat the cathode, an electric current can pass through it. So now you have a toggleable switch. If you have a little glass bulb without any air in it, a cathode that can be heated, and an anode plate, if you turn on the heating of the cathode through one method or another, you can pass an electric current through it. So now you have a toggleable switch, and those can be put together to create gates and turn inputs into outputs. So you have a computer. The problem is the number of switches you will need to create a computer that can do basic calculations adds up really quickly. So imagine 1,000 vacuum tubes in one device. That's not a very powerful computer, but it would take up an entire room. So that's how computers were back in like the 40s. They solved this problem with the transistor, where instead of it being a device that could be toggled, it was a material that could be toggled. The transistor is it's a tiny little silicon bit that has N-type silicon, and their 2 halves are divided by a strip of P-type silicon. N-type has extra electrons because it's been doped with phosphorus, and P-type is has a bunch of holes where electrons should be because it's been doped with boron. So if you have a diode where it's N-type and P-type, electricity can only pass from the N-type to the P-type. It can't pass the other way. So what happens if you have N-type, P-type, N-type? Well, you're not going to be able to pass electricity through that unless you neutralize the NP beginning diode by passing electricity through those. So you have to turn on a switch in order to make the transistor conductive. So now, just like the vacuum tube, you have a switch that can either conduct electricity or not because it's toggleable. I drew a little diagram of a very simple calculator. It can add numbers 1, 2, or 3 to numbers 1, 2, or 3. It needs 9 transistors, and it has 5 possible outputs. These transistors are AND gates, so you need both of these inputs to be on to get an output from it. There is one possible combination of these numbers that equals 2. There are 2 possible combinations of these numbers that equals 3, 3 possible that equal 4, 2 possible that equal 5, and 1 possible that equals 6. And if you follow these back, these 2 bring you to different combinations. Like if I add 2 and 2, that brings me to a 4. This specific 4, or one of these specific 4s, if I add 1 and a 2, I get brought to a 3, etc. So one of these AND gates gets activated. It will light up one of these. So I add 2 and a 2, that lights up one of these 4s, and that turns on this output. It's a very simple calculator. It can only add numbers 1, 2, or 3 to numbers 1, 2, or 3. But it needs 9 transistors, because there are 9 possible combinations of those specific inputs. 3 starting inputs that can have 3 possible following inputs each. Needs 9 transistors to handle that. So if you have 10 inputs, numbers 0 through 9, you're going to need 100 transistors to do the very, very simple task of adding numbers 0 through 9 to numbers 0 through 9. The reason we have to scale that down as small as possible is pretty obvious, but if you have enough transistors, you can do any number of operations a second. The human brain, I think, is somewhere between 8 and 10 quadrillion operations a second, which is very fast, but the fastest computer I think we've made is 3 times faster than that, 4 times faster than that. It's insane. But those supercomputers are fast. They're not smart. They can't think like a human can think. So then we have technologies like artificial intelligence, which are made to replicate human intelligence. There are 3 kinds: ANI, AGI, and ASI. The first is ANI, Artificial Narrow Intelligence. It's pretty straightforward. It's just a computer that can do one task really well. So a computer that is super good at playing chess but can't really do anything else. You can't have a conversation with that computer. And there's AGI, Artificial General Intelligence, which is the most analogous to a human brain. It can learn and adapt to do different things. It isn't made to do a specific thing. It just can do a bunch of different tasks. Then there's ASI, Artificial Super Intelligence, which is the scary kind. That's so intelligent that what ants are to us, we are to it. It can improve its brain exponentially, and it can solve any problem. It takes a look at you, it thinks, okay, Well, from that look, from the location of every single one of your cells, in a second I know how to make you live forever. Like that, that's the level it's on. It can take any information and create any output from that information. Futurist Ray Kurzweil says that computers will become as intelligent as us by 2045. This event is called the singularity, and it's either when all our problems get solved, or it's when we get terminated. The implications of a computer that's smart are scary. But there's really no limit on how smart a computer can get. Some people have come up with concepts like the Jupiter brain, which is a computer the size of a planet. Basically, so smart that it can simulate every thought every human has ever had. It's a spooky idea, but it raises some philosophical questions. Obviously, there's the simulation argument, we've all heard that, but there are other implications that it carries, like, let's say morality is based off of whether or not we do what others want, if that makes sense. Like, it's bad for me to hurt someone because they don't want to be hurt. If they wanted to be hurt, it wouldn't really be bad to hurt them. Or at least, if it was beneficial to them to hurt them, then it wouldn't be bad to hurt them. It wouldn't be hurting them. So let's extend that logic to a Jupiter brain that is the equivalent of hundreds of quadrillions of human brains. Whatever it wants is what it is morally right for us to do. Because, like, just how it's wrong for me to punch you in the face because you don't want me to punch you in the face. It's wrong for us to not do what that Jupiter brain wants because the equivalent of punching hundreds of quadrillions of humans in the face. So, really, that computer would define what is moral and what is not moral. A scarier way of putting that is that computer would become God. So let's say that Jupiter brain one day decides it wants to torture every human to death. That's what it wants to do. It would be morally correct for us to submit to it. It would be selfish and evil to not let it do that because it would do more harm to resist. It would hurt that poor Jupiter brain. It would be excruciating for us to not submit to it. Anyway, I'm Elijah from my parents' basement.